Okay, this is the solution to the problem I like to call the bucket problem. And I like this problem because it's almost deceptively simple. It's really easy to see the problem and say, oh, you're raising a bucket by a rope. The tension in the rope must be the weight of the bucket. So it must be mg, which is 10 kilograms times 10 meters per second squared, or 100 newtons. But in fact, it's not that simple. Because that's not the tension in the rope. That is actually the force due to gravity. To find the tension in the rope, I really strongly recommend that you do not just try and shoot from the hip here. Practice using our method. And our method that we have so far is to say that we're going to choose the object, we're going to choose the bucket, and we're going to draw the forces that are on the bucket. Because what we really want to do is use this idea that the sum of the forces on the object, not by the object, on the object, is equal to the mass of the object times the acceleration of the object. So we're going to draw these vectors. This is the force due to the rope. This is the tension. And this is the force due to gravity. I'm going to choose axes, x and y, and then I'm going to apply Newton's second law. So I only need to worry about the y direction, and the sum of the forces there is the force due to the rope in the positive direction and the force due to gravity in the negative direction. And that's equal to m times a. So the force due to the rope, the thing that I'm trying to find, minus mg. Now I want you to notice here that I've already put the minus sign in. Okay, so that means that g is just a number. It's 10 meters per second squared. So I'm automatically putting in the direction here as negative because of the axes I chose. Do not make g a negative number, because then you have two negatives, okay? And the reason is that we could have just as easily chosen the positive direction downward and we get the same answer. Okay, so minus mg is equal to m times a. And because it says that the bucket is being raised and it's speeding up, that means that the acceleration is upward. Notice that I do not draw the acceleration on the free body diagram. I draw it off to the side with a funky looking arrow so that I don't get it confused. On the left-hand side are the forces on the object, and on the right-hand side is the acceleration of the object. So now the force in the rope is equal to, I add mg to both sides, and I get mg plus a. So this is 10 kilograms times 10 meters per second squared plus 2 meters per second squared, which is 12. So the total is 120 newtons. So I mentioned that I could have done this problem with the axes pointing in the other direction, and I want to actually show you that right now, just so that you believe me. If I had chosen axes that go with the positive direction downward, this free body diagram is still the same, only now the tension in the rope is upward, gravity is downward, and now the acceleration is negative 2 meters per second squared. So when I do that problem, I get that the tension in the rope, so negative tension in the rope, is minus mg minus ma. If I multiply through by minus 1, tension in the rope is equal to mg plus a. Okay, so I get the same answer no matter which axes I pick. Now what about if you were lowering the rope? What if you were speeding up while lowering it? What if you were slowing down while lowering it? Slowing down while raising it? All of these are worthwhile circumstances, and you should think about what those are, and we'll pick it up from there next time. See you then.